Hello everybody. My name is Manuel La Rosa Betancourt. I am co-founder and CEO of Neutron Star Systems. And Neutron Star Systems is one of the partners for dissemination and exploitations of results of the MEESST consortium. MEESST stands for Magnetohydro Dynamics Enhanced Entry System for Space Transportation, and it is a project funded by the European Innovation Council under the program Pathfinder. And here today with
Alan Viladegut.
Thank you very much. Alan, can you introduce yourself?
Yes, thank you for bringing us this opportunity to explain to the audience what we do here. So, I'm Alan Viladegut. I'm research engineer here at the Karman Institute, and I'm taking the lead on the work package number 2 in the MEESST project, where we basically deal with the plasma wind tunnel laser experiments that we will prove the technology for the re-entry system that we are developing here.
Great. Alan, 3 years of the project, a lot of things have happened. Tell us, how has been your experience in the project so far?
So it's we have faced several challenges. I must say the experience has been there are ways where the experience has been very good because it allows us to introduce the von Karman Institute to new research domains. These research domains can be the radio blackout in our case, where it's a domain that it was completely new to us. But so far the positive outcomes of this project has been that we already triggered new synergies with other institutions that allow us to continue the research to continue developing on this technology.
Okay, and can you tell us a little bit of how's the dynamics of interaction within the consortium, given the fact that we have a pandemic and given the fact that we have also a war? Do you have any impact on the execution of the project because of this?
Well, the impact has been, it's quite clear. So first we suffered delays on the procurement of the probe that we will start testing today because of other partners couldn't provide the materials in time or the resources in time. So in that sense we suffered these delays. On our side, on the preliminary campaigns we did before, we also suffered some delays because we could, in the COVID period, we could not enter freely into the lab. Interaction has been was minimal through homeworking experience, etc., which made difficult the interactions in the lab, which clearly you need a person-to-person interaction.
Absolutely.
Yeah.
Okay. Thank you. Tell us about the most interesting or biggest technical challenges you have had. I mean, regarding the work package VKI was executing within the project.
So one of the as you know, Manuel, we have 2 experimental campaigns in the future. One is here at VKI with our plasma wind tunnel, but we also have the IRS plasma wind tunnel, and coordinating the activity inside the experimental work package, we had to coordinate the compatibility of the interfaces to enter the 2 vacuum chambers together with Absolute Systems and with KIT, and this was one of a big challenge because the 2 facilities, we realized that even though they try to reproduce the same environment, they are completely different and quite different. Yes, indeed. Another technical challenge, of course, for us was to measure for the first time signal attenuation and radio communications through using the plasma facility. So, as you know, this plasma facility offers us the opportunity to test with an ionized flow, and thanks to this, we measured already some attenuation in the radio signal. So this gives us, let's say, we are optimistic in the results that we can get from the MEESST.
Sounds good.
Yeah.
Just to try to involve at the general audience on this dissemination activity we're doing. When you say radio attenuation or signal attenuation, can you explain in layman's terms for the general audience what is exactly what you're trying to say here?
So basically, what we do here in the plasmatron is to reproduce the re-entry conditions of a spacecraft. This means that there are free electrons in the surrounding the spacecraft because we dissociate the gases, etc., due to high temperatures. And because the presence of these electrons, what it affects is that it interacts with the radio signal that you try to transmit, and at some point the content of these electrons is so high that you prevent the communication to go through the gas. So
Right.
actually there is a period of time where you cut the communications with your re-entry system.
That's what
And
you
this
call
is-
blackout.
And this is what we call indeed blackout. It can take, depending on the re-entry trajectory, it can take from seconds to maybe minutes. But this is something that we are trying to solve in the MEESST project.
Excellent. Thank you very much. What is in your opinion, the biggest achievement that you expect to get at the end of the project?
Also prove the technology in the sense that by using a magnetic field we can rearrange the electrons in such a way that we can transmit the signal, but also I hope that at IRS they can demonstrate also that they can reduce the heat flux that is impinging on the stagnation point of the capsules by using the same magnets. So actually it's kind of a
Twofold expectation or twofold
yeah.
achievement.
Indeed.
Just to keep the audience with us. I understood that one is to demonstrate that we can get signals through the plasma
Mm-hmm.
to communicate with ground control,
Mm-hmm.
and then the second achievement, reducing the heat fluxes that impinge
Yeah.
the capsule during re-entry. What exactly that means for someone who is not from space?
So basically, when designing a re-entry system, we always have to think on a thermal protection system. Means that when we re-enter, we have hot gases, or we will generate hot gases around the spacecraft, and in order for the payload to survive, we need to protect it with specific materials that can sustain very high temperatures
Okay.
or high heat fluxes. Okay.
And the idea is to reduce these
So
heat
the
fluxes?
idea is to use the magnet to again modify the flow in front of the spacecraft, and by modifying the flow in front of the spacecraft, the temperatures are surrounding the capsule will be lower.
Okay.
Hence the chances of survivability are higher, much higher.
Okay, and what is the impact of a lower temperature in terms of the capsule architecture or the capsule construction?
So basically, we look for optimization here. So normally, in the industry, we use quite conservative standards to design the thermal protection systems, meaning that we use very thick layers of insulators.
All right.
With this technology, what we expect is that we will be able to reduce these layers of insulation, so that the thermal protection system can be much thinner, and therefore reduce the weight of the thermal protection system, and therefore we could increase the payload that is on board of the spacecraft.
Excellent. So you want to increase payload capacity,
Yes.
reduce the weight of thermal
Mhm.
protection systems,
Mhm.
enhance radio communications
Yeah.
during re-entry. I see that, it's a quite ambitious goal.
It is.
Well, Alan, thank you very much for your time, and I appreciate the explanations you have given for the audience. Thank you very much.